Let's move on and look at a new example that falls under the strategy of expansion problems. So for example number 3, let's investigate the limit. As h approaches 0, we'll have quantity 5 plus h squared minus 25 all over h. Now this might seem like a fairly arbitrary limit problem, but this one actually has a lot of importance for the work of developing the derivative that we're going to do shortly. So anyways, the skills that we'll see on this problem are really important. Now, we have the same situation that if we tried to just use direct substitution and plug in 0, we have this denominator problem of 0, and the numerator is also giving us a value of 0. So essentially what we're starting to see is a pattern emerge that the reason we're not getting a value by direct substitution has to do with this problem of dividing by 0. So in all of these instances, we're essentially employing a strategy that helps us fix the problem. With factoring, we found a way to cancel the factor from the denominator that was producing the problem. With this, we're going to find another way of doing very much the same thing. So let's go ahead and expand. You might want to recall, maybe off in the side here, that 5 plus h quantity squared represents multiplying 5 plus h by itself, and we'll need to use the proper techniques of multiplying those binomials. In the end, we're going to get 25 plus 10h plus h squared. Now those parentheses are no longer essential, but I'll put them here just to help you categorize what we've got going on. Remember, our goal is to get rid of this h. And now that we've expanded, once we start to simplify, we can see that those terms will subtract. And the new version of our limit is 10h plus h squared over h. And in all of these problems, once we do a little bit of this simplification work, we're going to see that this problem of h in the denominator can be resolved as we divide it into each of the remaining terms. So dividing h into those terms gives us 10 plus h as a simplified expression. We've fixed the problem by removing that factor of h through division, and now we can evaluate this limit back to direct substitution. Let's look at one more example that's a little bit involved. If you're feeling like you did pretty well on that last one, you might want to pause the video and try this one on your own, and then you can check your work along the way. So this time I'm going to put a coefficient of 4 on this expression, 3 plus h squared minus 36 all over h. And it's a good exercise for you to verify that if you plugged in 0 for h, both the numerator and the denominator again return 0 over 0. We've got this problem. We're going to fix it in pretty much the same way. Now, like the last example, when we have this quantity of 3 plus h multiplied by itself, we should start, maybe just for our convenience, in multiplying those binomials together, and then we'll distribute a 4 through the remaining terms. So what I'm going to get with this first expression being simplified is 36 plus 24h plus 4h squared. A little bit more algebra to keep track of, minus 36 all over h. And you'll see a very similar parallel structure from the previous example. In much the same way, I will subtract off those constants. The term that I'm left with in the numerator will again be divisible by h, 24h plus 4h squared over h. And just like before, I can divide each term in the numerator by h, and I'll be left with essentially what represents a continuous function, and we can investigate the limit now by direct substitution.